We have talked about binary numbers, the basics of binary numbers, binary conversions, and so we basically understand what binary numbers are. What we want to do now is discuss this. See, not everything in a machine, in a computer system, in a digital system is necessarily a number. And even if it is a number, that number is not necessarily a binary number. Okay? That's what we are discussing now. We are talking about codes. Okay? And there are different coding systems. These coding systems represent signed numbers, unsigned numbers. So signed numbers means a number that has positive and negative versions. Unsigned numbers means that a number that is only positive. But then an unsigned number is not necessarily just a binary number. Okay? And so there are other representations. There are many, many coding systems. There are coding systems for error correction, meaning that if there is a fault, there is a problem in the transmission line of data going from one place to the other, and if there is a bit that is flipped, these error correction codes do have the capability of correcting the bits that are wrong to some extent. We are not discussing those, but all I'm saying now is that we have to talk about codes. And in a computer system, in a digital system, you see ones and zeros. These may be codes. We start with a very basic thing, which is signed numbers. See, so far what I have said is here is a number, which is a positive number. Okay, we said 1001001 is a positive number, and then the question is, how do I represent the negative number? Remember that the only thing we have is either a zero or a number or a one. We don't have a choice. The only way we can represent this positive, the negative of 73, is to use a 1 or a 0. The convention is the following. We use a bit. Let's say this bit here. If this bit is 0, then we say this is a positive number. And if this bit is 1, we say this is a negative number. It's always like this. Positive numbers are represented by what is called a sign bit, which is 0, and negative numbers with a sign bit that is a 1. The question is, where do we put this bit? Okay, do we put it on the right hand side? No, we don't do that. We put it on the left hand side. So this becomes the sign bit for my number here. But then, if it is a sign bit, then how do I not get it confused with the regular bits of the number? Okay, that's where word length comes in. Before saying this is a sign bit, I have to decide how many bits this entire number has. Okay, so here I'm saying this is an 8-bit signed number. I'm not done yet. I haven't said everything yet. I'm saying this is an 8-bit signed number. Okay, what it means is 1, 2, 3, 4, 5, 6, 7 of the bits represent the magnitude of the number, or somehow the magnitude of the number. And the last bit, the 8th bit, is the sign bit. If I had said to you that no, this is a 16-bit signed number, it would mean that the number would be 1, 2, 3, 4, 5. 6, 7, 8, 1, 0, 0, 1, 0, 0, 1. These are 15 bits altogether, and then the sign bit would be this. That is if I had said this is a 16-bit signed number. There are two representations for signed number. One of them is referred to as sign and magnitude. That's the easiest. That at least this is the one that seems to be the easiest, but then we will see later on that this has a lot of problems. Let's not worry about that for later on. Until later on. I'm saying a sign and magnitude representation is as simple as if it is an n-bit number, n minus 1 bits represent the magnitude in binary. The magnitude in binary. And then the leftmost bit is not part of the magnitude, is the sign bit. A 0 for plus, a 1 for negative. So what I'm writing here is plus 73 in 16-bit sign and magnitude representation. What I have here shown in this is plus 73, again plus 73 in 8-bit sign and magnitude representation, and the one below that is minus 73 in sign and magnitude representation. Okay? And if you want to know the magnitude, just convert it to binary, and then this is all you need to do. So the leftmost digit is always representing the sign. Let me tell you this. There will be other representations for negative and positive numbers, or more briefly, for signed numbers. In those representations also, 0 is for positive, 1 is for negative, even though the whole system is entirely different than what we are discussing here, but then still the sign bit is 0 for positive, 1 for negative. So this is plus 73, minus 73, and then there is always a sign bit. And so if you have a fractional part also, then you dedicate 1 bit to the sign bit, and then the rest of it is your magnitude. So for example, I can say here is a let's say 32-bit fixed point sign and magnitude signed number. And then this fixed point, we are using, let's say, 8 bits for the fractional. What it means is that there is this binary point after the 8th bit. Okay, then we have 23 bits for the integer part, and then always 1 bit for the sign bit, and then that 1 bit is either 0 or 1 for positive or negative. And usually that is put on the left-hand side of the number. Okay, and therefore this is 23 plus 1 bit here. This is the integer. This is the fractional. And this is the sign bit. Okay. And this is, the whole thing is 32 bits. This is fixed point. Fixed point meaning that there is a point, a fixed point, imaginary point, where you draw the line between the fractional part and the integer part. All right, so now we know how to represent numbers, positive and negative, fractional and integer. Let's say something else. Not all numbers in a computer system are necessarily for representation of numbers. Not all numbers are necessarily numbers with fractional part or integer parts. Maybe there are, in a computer system, there are phone numbers represented. Okay? And phone numbers, you don't need to represent them in decimal. You don't need to do arithmetic. You just need to represent them in a form that you can easily distinguish the digits. If I take a number, let's say in Massachusetts, 774, okay, 555, 1234, that's a 10-digit number. And I want to represent it in binary. If I represent it in binary, remember the division process, divide by 2, divide by 2, divide by 2. You can eventually do that, okay? But then there will be many, many bits for representing, which is fine. But then if I ask you, go and identify numbers in Massachusetts, then those bits are so mixed, are so intermixed, that you have to turn them into decimal to be able to say, well, these are in Massachusetts. Okay? Alternatively, instead of taking the entire number, turning it into binary, what I can do is do one digit at a time. The digits are between 0 and 9, and if I want to do one digit at a time, I have to do 0 through 9. I require 4 bits, even though I'm not going to have 10, 11 to 15, but then 0 through 9, if I want to do one digit at a time independently, I need 4 bits for each digit. So this is what I'm going to do. I'm going to, these are numbers in Massachusetts, 774. Okay. Or maybe this is the exchange. You still want to identify that. If you take this number and individually turn them into 4 binary digits, then it becomes like this. 7, 7, 7, 4, 5, 5, 5, 1, 2, 3, 4, 2, 3, 4. Okay? Obviously, this is going to take more room than if I were to turn this into its equivalent binary number. I'm using more bits. Why is it? See, because in 4 bits, 0, 0, 1, 0. Okay. In 4 bits, I'm representing only 0 through 9, whereas if I turned it into binary, 4 bits could give me 0 through 15. So I am really not utilizing all the power of all the bits that are there. That's okay. But then what happens is that if you ask me, what are the 555 numbers? I know that they are sitting here, here, here. I can very easily circle this and say, well, these are the 555 numbers. What are the numbers in Massachusetts? Well, those are the numbers in Massachusetts, or 774 in Massachusetts, are those that have the leftmost 12 bits follow this particular pattern. 0, 1, 1, 1, 0 1 1 1 0 1 0 0. Okay, that's the pattern that is following. And therefore, the number can easily be identified according to the pattern. But see, this is not binary. It's not exactly not binary. It's a binary that individual decimal digits have been turned into binary. So we call it binary coded decimal. Okay? And it gives it 4 binary bits, 0 through 9. Okay? These are the decimal parts, but these decimal digits are turned into binary independently. This is good for phone numbers. This is good, let me tell you this, for old calculators where you would press 1, 2, 3, 4, 5, and it would take a lot of hardware for turning the numbers from what you enter into the internal representation of it. What they did, those old calculators, what they did, they would represent the numbers in BCD, and then all they needed to do was adding and subtracting and basic operations. And for those BCD procedure for adding and subtracting was there. But then when calculators become more complex, doing the operations in BCD would be way more complex, and therefore the interface changed significantly. So what we are saying here is for phone numbers and for places where you like to have direct decimal to binary translation conversion. All right, there are a lot of places in places where you have a counter, a 4-bit counter, or you have 4-bit numbers that you want to represent them. And you have seen these 7-segment displays in a lot of places, these things here. In order to display a number on this, if I want to have, for example, 1 displayed on this, I have to set segment B and C to 1, or turn on segment B and C. If I want to have a 0 there, I have to have segments A, B, C, D, E, F turned on. Okay? If I want to have an 8 represented, I have to have all of them on. This thing is called a 7-segment display. The code that turns this into numbers is called 7-segment display code. Okay? And this particular code is only used for this simple display. A lot of displays are, because it's simple, because it's so easy to build a circuit. Maybe if you're doing some hobby circuits or something like this, you use these 7-segment displays. 7-segment display goes like this. The code for 0 is those segments that display a 0. Therefore, a 0 is this. Let me do red to indicate that they are on. So this, and this. These segments. I could do better. That's 0. That's a 1. That's a 2. That's a 3. Okay. That's a 4. And continue on this side. This is a 5. This is a 6. There are 2 ways we can write the 6. This is a 6. This is 7. So we can have this top part of 6 not turned on, but then here we only have 1 0, which is segment B. This is 7. 8 is easy. And 9 is also like 6. There are two ways of doing it. I can have segment D on or off. So this becoming 0 is also okay. All right, so this is called a 7-segment display code. Why do we use a 7-segment display code? Only for turning on numbers, and those are numbers, BCD numbers, meaning numbers between 0 to 9 on one of these 7-segment displays. So if I have a 8-bit number, a binary 8-bit number, I want to display that on a 7-segment display, I have to turn that 8-bit binary number to 3 BCD digits first, and then do a BCD to 7-segment display conversion. A circuit that turns a BCD number into a 7-segment display code is an integrated circuit, a very, very old one used by hobbyists very often, which is 74 LS74. We will talk about these little packages, packages that used to be very common, but then now they have been replaced by integrated circuits, FPGAs, and so on. So what you do is you put a BCD on the inputs, pins number 7, 1, 2, and 6, and then it will display whatever BCD number you have on the outputs A to G, and then there is a decimal point also. If you want to use that, and but then actually display A to G, and then display A to G, connect to the pins of the SSD display thing, and it will show the proper number. All right, there is this other thing, which is another coding system. See, we are talking about coding systems. So one code to the other to the other. Another coding system is called gray code. See, this is the story. The story is, I have a processing element. Okay, let's make the story a very short, a very simple one. This processing element takes inputs, a binary input between 0 and 15. Okay, this is the least significant bit meaning the bit that has the lowest value. This is the most significant bit, number 3. This processing element is looking at the input, and based on the input, it's making certain decisions. Maybe it's looking at the wind velocity, maybe it's looking at the temperature or something like that. And based on that, it's making certain decisions. If it is a wind velocity, it wants to turn on some gauges, some valves or something. If it's a temperature, it is looking at the temperature and turning on air conditioner or something. Okay? Let's say for now that like I said, the temperature is between 0 and 15. The temperature is 0, 0, 0, 0. That's number 1. And then the temperature turns to 1. Then the temperature turns to 2. At one point, the temperature turns to 0, 1, 1, 1, which is 7. And then it goes up, becomes 8. And then goes up, becomes 9. My system, my processing element is looking at these inputs and saying, okay, the temperature went up from 0 to 1, so let's make certain decision. And then it says the temperature went up from 8 to 9, so let's make certain decisions. Okay? At one point, my system looks at the temperature, and the temperature is 7. Temperature goes up. Okay, temperature goes up. That means the 0 on the left has to change to 1. The ones on the right have to change to 0. But see, I have no clue as to which one of these bits change first. On this side, I have a temperature sensor. And then I have signals going from the temperature sensor into perhaps an analog to digital circuit. The analog to digital circuit is an electronic component, and then there are transistors there are resistances, there are capacitances there. And then the output of the A to D is, that's the analog to digital, is being transmitted to my digital system here, my processing element. So there is no guarantee that bit 0 changes, or bit 1 changes, or bit 2 changes, or bit 3 changes first. Anything can happen. Actually, not only that, if today bit 3 changes first, tomorrow it may be a different story. Okay? Tomorrow may be a different story. Maybe bit 2 changes first, because the electronics is sensitive to humidity, to the aging, to the temperature, and lots of other things. So, changing from 7 to 8, maybe this bit changes first. It becomes 0, 0, 1, 1. Okay? And then the bit to the left changes next. 1, 0, 1, 1. It's all in the direction of changing all bits from 0, 1, 1, 1 to 1, 0, 0, 0. But then these are changing because of the physical properties of wires and electronics. I cannot count on that. And then the next bit changes. 1, 0, perhaps 0, 1. And then finally, this changes to this. What is my processing element is supposed to do? My processing element has no idea that these are delays and these are temporary transitional values. My processing element looks at this, it sees a 7. It sees a 7. Okay? You think the next number is 8. But that's not what my processing element is seeing. My processing element is seeing 3. Then my processing element is seeing 11. Then my processing element is seeing 9. And then it is seeing 8. When it's 7, all of a sudden it sees the temperature dropped significantly, so it has to react. Maybe the reaction is something critical. Okay? But then, all of a sudden, the temperature goes all the way up to 11. Because these are transitional numbers, and my processing element has no clue that these are transitional values. It thinks these are the actual values, and based on those actual values, it starts reacting. But then soon, one changes to the next one, then it completely confuses my processing element. Why didn't something like this happen when you were going from 1 to 2? Why didn't this happen? Because there is only 1 bit difference between the number 1 to 2. Why doesn't this happen when you are going from 8 to 9? Because between 8 and 9 there is only 1 bit difference. So why don't we do this? Why don't we come up with a system of number that between every 2 consecutive numbers there is only 1 bit difference? So let's come up with a numbering system like this, and I call that gray code system. This is my numbering system. 0, 0, 0, 0 represents 0. 0, 0, 0, 1 becomes 1. 0, 0, 1, 0 is 2. 0, 0, 1, 1 is 3. I'm sorry. 0, 0. 1, 1 is 2. You say this is 3. No, I say in gray code this is 3. 0, 0, 1, 0. Okay, that's 3. Let me write everything down before, and then I go over it. So it is okay. Look, this is 0, this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. Now look at every two consecutive numbers, for example, 7 and 8. There is only 1 bit difference, so there is no way for you to confuse my processing element. If it's 7, it is 0, 1, 1, 0, 1, 0, 0. If it's 8, it changes to 1, 1, 0, 1. There is nothing between these two. You can only go from 7 to 8. You can only go from 8 to 7. Nothing in between them. No blue values between them. And therefore, my processing element is not going to get confused. Not only that, between the first number and the last number, there is also only 1 bit difference. That means if my input is going from 0000 to 15, 15 becomes 1000 and rolls over back to 0000, there is also 1 bit difference. Okay? If you want to remember this, see the first, look at the first column. The first column has a 0 and then 2 1s, 2 zeros, 2 1s, 2 zeros, and so on. The second column, do this. The second column, instead of 1 0, 2 zeros, but then 4 1s, 4 zeros, 4 1s, 4 zeros. Now, if you have 5-bit gray code, then you can just write those down too. Third column, you start with, instead of 2 zeros, you start with 4 zeros, then 8 1s, 8 zeros, and so on. All right. Then there is another coding system. Another coding system we refer to as XS3 coding system. If these digits were BCD numbers, meaning between 0 to 9, okay, these are single digit decimal numbers, then the first number would be 0, the last number would be 9, and then you go from 0 to 1 to 2. When you go from 9, roll over back to 0 so that the next digit increments. Then you have from 9 to 0, you have 3 bits different. Look, you have 3 differences here. This is 9. This is 0. And therefore, between 9 and 0, you have 3 differences. And therefore, you have the same problem. That's if you are doing BCD. You like between 0 and 9 to also be only 1 bit difference. I'm going to do this. I'm going to create a new system, a new coding system. My new coding system calls this one a 0. 3 is a 0. Then this is 1, 2, 3, 4, 5, 6, 7, 8, 9, and this is 9. Now look at the difference between the number of ones with the new system I have, which I'm going to write that in dark red. This is my new 0. 1, 2, 3, 4, 5, 6, 7, 8, 9. Not only between two consecutive numbers I only have 1 bit changing, but also between the first number, which is 0, which is 0, 0, 1, 0, and 9, which is 1, 0, 1, 0, there is also 1 bit difference. This coding system in dark red is called XS3. That means is the gray code added 3 to it. Okay? So this is the key thing. When you see a 0, Okay? Or when you see somewhere in your digital system 0000, that's not necessarily 0. That's not even necessarily a number. Okay? That may be a notation. And even if I tell you this is a number, this may be a positive number. It's maybe a signed number, maybe a complete different representation of number, or maybe it's a gray code, maybe it's an XS3 system. If I tell you 0000 and tell you this is an XS3 system, then you say no, it cannot, because XS3 system goes between 0010 all the way to 1010, and no 0000 exists in the XS3 system. All right, so gray code system goes like this. Between 7 and 8, it should have been. Okay. There are intermediate numbers. In order to avoid that, you come up with a coding system that every 2 consecutive numbers are only different in 1 bit, which is what I'm showing on the right-hand side here. Lastly, in the coding system, like I said, when you see a string of ones and zeros, 0, 1, 1, 0, 1, 0, 1, let's put another 1 here. If you see this, and I ask you, what is this? You don't know. I have to tell you whether this is a number. If I tell you this is a number, this is maybe a complete 8-bit number, maybe not. Maybe this is part of a 32-bit number. Or maybe this is not a number at all. Maybe it's a code. Maybe it's a coding system of some sort. Or maybe in the digital system you're looking at this, this is really a character. How do we represent characters? There is this ASCII, American Standard Code for Information Interchange. This has evolved over the years. It used to be only uppercase characters and numerals and things. Little by little, it has now become an 8-bit coding system. This is called ASCII. ASCII is like this. The table I'm showing on the right-hand side is really the left-hand side part of the ASCII. In this part, the leftmost bit is 0, but then we have extended ASCII. Extended ASCII. The right-hand side, the leftmost bit is 1. Look at the number I have. 0, 1, 1, 0, 1, 0, 1, 1. What is this in ASCII? First of all, because the leftmost bit is 0, it fits in the ASCII table, means it is something in my table that I'm showing. Then it is 110. 110 is 6, and therefore it is in the 6th column. And then it's 1011. 1011 is 13. 13 is D, and therefore this is little m. Okay? How about the ASCII, extended ASCII? Well, extended ASCII is something like this, but then foreign characters like, for example, the N with a hat on it, or U with dots in Germany, or other characters are represented in the right-hand side. Okay? Let me explain a few things about ASCII. The very, very first code is null, means nothing. Okay? What it means is if you receive a 0, 0, 0, 0, 0, 0, 0, 0, that is this, and that's null, as if nothing has happened. The very last code here is 0, because it's in the left-hand side table. It is in the not in the extended ASCII, so on the leftmost bit is 0. And then 111, that's 7. F1111, and this is the delete character. So when you press delete, whatever software you have sends out a code 01111111 to your terminal, and terminal deletes the character under the existing cursor. That's different from backspace. Backspace is this one over here. Okay, so backspace is 0, 0, 0, 0, and 8, 1, 0, 0, 0. Okay, that's backspace. All right, the first two columns are called control characters. The next column is called, use my highlighter here. The next column is starts with the space, and then there are special characters. These are special characters. Then the next column begins with 0, goes to 9, and then down below again there are special characters. The next column starts with @, which is a special character, goes with the capital E all the way to capital Z into the next column, and then we have again special characters. The next column begins with single quote, which is a special character, goes to A through Z, and then again we have special characters. Control characters are nice, are funny. Control characters, the first two columns, null, SOH, STX, ETX, EOT, this, and that. These were originally named for very, very old teletype machines, old technology machines. Some of them I remember, for example, EOT, end of tape. Bell, still used, which is the bip now. Okay, but then there was a little bell in your terminal that when it got to the end of the line or something happened, the bell would ring, and therefore quote the 7 is a bell. Line feed. Okay. Carriage return. Carriage. What is a carriage? The return key. That was because it used to be a carriage. It was a carriage. It was a thing on the typewriter, on the teletype, that would go all the way to the left. That was called CR, or carriage return. This is now return. Form feed, and so on. Escape, and so on. Because these names are old and some of them don't apply anymore, in order to remember these names, in order to identify these control characters, they are identified by the character on the same row. For example, instead of saying backspace, I say Control H. Instead of saying this is a bell, I say Control G. EOT is Control D. Form feed is Control L. Carriage return is Control M. Okay? Escape is Control square bracket. And some other ones. Okay? These are the characters. A lot of these are for handshaking between the machine and the computer. The machine was fully mechanical. So when you send a character to it, it would say, wait, don't send me the next character until I get this printed. Once it gets that printed, then it would free the line. So this is acknowledge. Okay? You don't need to remember these, but know the source of them. But then if you hear Control E, it means this code. So Control E is 0, 0, 0, 0, 0, 1, 0, 1. That's Control E, and often written with the hat on top of the E. All right. we have covered coding systems, and what we want to do next is arithmetic. And I guess this is a little bit more explanation about the ASCII. This is extended ASCII and so on. Next is arithmetic.